Good morning, everyone. Welcome to the penultimate lecture of STEMS 2022 Qualifier Camp, conducted in coordination with Raising a Mathematician Foundation. I hope this has been a great learning experience for all of you with several great lectures. So today we are honored to have Professor Suresh Nayak with us. Professor Suresh is an associate professor at the Stats and Maths Unit of Indian Statistical Institute, Bangalore. His research interests are primarily in algebraic geometry and commutative algebra. He received his BTech in computer science from IIT Bombay and his MS in PhD in mathematics from Purdue University. In today's lecture, we will explore more on a very fundamental topic in algebra, namely factorizations and primes in context other than just natural numbers, which all of you are familiar with. Hope all of you enjoyed the talk. A quick comment before we begin the talk. Please use the chat box for your questions or raise your hand, and the moderators will take up them with the appropriate time. Over to you, Professor.
Okay, thank you. Thanks for the opportunity to speak here. And hello, welcome everyone. So today's topic, as you can see, is factorizations, primes, and points. So we will start with basic results which are familiar to us from school days about prime numbers and factorizing integers into primes. And then slowly from there, we'll move on to other contexts and see what are the properties of these factorizations. So let's see. So I'll begin here. So here's the first statement, which we are all familiar with. So I hope the handwriting is legible to everyone. You can read it?
Yes.
Okay. So the theorem is it's unique factorization for integers, and my notation for integers is Z. And so what is it? It's every non-zero integer n factors uniquely as a product of prime numbers. So since I mean, if you want, you can insist on only positive integers, in which case you just put a plus here. So for negative, I put a minus here. And P1, and here I allow the prime numbers to repeat. So for example, 60 is 2 times 2 times 3 times 5. All right. A very similar result, which again, we are familiar from our school days, is factorization of polynomials. And in this case, I will simultaneously take 3 cases which are all similar. One is the most familiar to us, the one we start with is polynomials over real numbers. And then I assume all of you are familiar with the notion of complex numbers. So this involves square root of -1. So you can look at polynomials over complex numbers or just simply rational numbers. So that's a very small set. And over that, you can look at polynomials. And let's look at the result. So I will use, So I'll use a common symbol for all 3 of these so-called sets of real numbers, or what we call them as fields of real numbers. So that's why I'm using the letter F here. F is either the field of real numbers or the field of complex numbers or the field of rational numbers. Fx is the set of all polynomials in X with coefficients in F. Then once again, you can factor it. You can factor any polynomial as a product of various irreducible polynomials. So these polynomials, you can't factor them further. The only thing is, if I want to get a strict uniqueness, what I have to do is, of course, I have to ensure that they all have degree greater than or equal to 1. So that they are non-constant, and the leading coefficient means the coefficient of the highest power of each pi is 1. And then f, however, the leading coefficient of f may not be 1, so I have to put a constant here. And this c is going to be non-zero. If I have assumed fx is non-zero, then this c is of course also going to be non-zero. So since I have I'm tackling all these 3 cases simultaneously, therefore one has to be a bit careful about what factorization will mean in this case. It will depend from the way you factor it will depend on the field in question. So for example, the same polynomial x8 minus 1, it has coefficients in integers, and therefore it has coefficients in all these 3 fields. Over rational numbers, you can factor it as x minus 1, x plus 1, x squared plus 1, and x4 plus 1, right? And but you cannot factor this further. I mean, you cannot split this polynomial any further over rational numbers, nor can you split this over rational numbers. But if you're allowed real coefficients, then you can in fact split this one further, and it breaks up like this. And if you're allowed one more step further, if you're allowed complex coefficients, then in fact you can also split this, and it becomes a product of two linear forms. And this also splits into four products here. They are all basically the 8th roots of unity, and these are the 4 8th roots of unity. So square root of I, basically, 45 degrees angle, if you're familiar with the roots of unity. So this is the factorization we obtain. And so note that the way you factor it into product of irreducibles will depend on the context here. So even though I'm simultaneously writing one theorem, really they are 3 different theorems in some sense. So one minor comment before we move on is what are all the multiplicatively invertible elements in these two contexts? So multiplicatively invertible elements is a long phrase, so I will use a shorter phrase which is used quite often: units. So what are the units in Z and Fx? So in Z, which is the integers, the invertible numbers are just plus or minus 1. And in Fx, the invertible numbers are just the constants. And those are the ones which are appearing here. And those are the ones which are slightly messing up your uniqueness part. But in fact, they are important because if you want to tackle all integers or all polynomials, you do need that. So, all right. So these are the theorems which we are familiar from our school days. And what is kind of easy or obvious from part in this theorems is the factorization part. I mean, you know how to factor this. Simply, I mean, for example, in the case of integers, simply check if it is divisible by any number smaller than itself. If it is not, then you know that it's going to be a prime. So you declare it to be a prime. Otherwise, you break it up as a product of two integers and then continue inductively, meaning for all those, both the factors, you again try to see whether they are primes or factor them further. And so factorization part, and similarly for polynomials, you see if it's irreducible, otherwise you try to factor it. So the factorization part is easy. What is not immediately obvious and somehow is, well, there's a reason for it, but we do not cover this in school, is why is this factorization unique? I think most of us take it for granted, at least in school, I used to take it for granted because you take any number or you take any polynomial, you factor it, that's what you get. And anybody else, you try factoring it tomorrow and you'll get the same factorization. And anybody else tries to factor it, you get the same answer. In fact, for small numbers, you can quickly see that this is the only factorization. But frankly, actually, it's not immediately obvious why the factorization is unique, especially if you are, some really big primes are involved, then it's not clear why I cannot find a product of some other prime numbers which will also give me the same answer. So there is some proof needed. And what I'll now do is I will go over quickly a sketch of how the proof goes. And then from there, we'll move on to other situations and see whether the same result or same principle applies.
A quick step. Yeah. There is one request to repeat the invertible elements and what units are in Fx and integers.
So invertible elements are those for which the multiplicative inverse also lies in the same set. So in Z, the invertible elements are those for which, an integer is invertible means that 1 by n should also be in Z. So obviously that is only possible if 1 by n is also an integer only if n is plus or minus 1. So that is what this plus or minus, this is actually plus or minus 1 appearing here. And similarly in Fx, a polynomial is invertible. Then if a polynomial is invertible, then it has to be degree 0, because if it's degree more than 0, it will not be invertible. You can easily check that. And so degree 0 means it's a constant. So that, oops, this goes into this eraser mode. Okay. So therefore, this is the, these are the invertible elements. So the invertible units in Fx are constants and in integers are plus or minus 1. Is that clear?
Yes, sir. Thank you.
Okay. So I'll now move on to the next page. And what we'll do is we'll try to prove the uniqueness part in these theorems. So we'll try to see why is the factorization unique. And then from there on, we'll move on to other contexts. Okay, so okay, let's do it here. To prove the uniqueness part, basically what one needs is the following prime property. And the prime property is the following. So for example, let's assume P, M1 and M2 are integers, but you can also think of them as P of X, M1 of X and M2 of X as polynomials. So it's the same proof which will apply to both the situations. So let's think of, let's look at integers first. So suppose P divides M1, M2. I want to, then I claim that P will either divide M1 or P will either divide M2. And this is again a property of prime numbers which we use quite often, but it needs a proof. Especially think of it as some very big prime. Then, I mean, some 10-digit prime, then it's not clear why if it divides product of two numbers, it has to divide one of them. So this is really the crucial property, because once you have this, then the uniqueness follows. Because take your integer n, or your, if you want, you can think of n as a polynomial. So take your integer or polynomial and write it as a product of primes in one way. And suppose you could also write it as a product of primes in another way. So Q1 to QL are also primes, and P1 to PK are also primes or irreducible polynomials, whatever you want to think of. Then what will happen is that take this prime P1 here, then P1 divides this entire product. But what it is saying here is that if it divides a product of two, and therefore if it divides a product of two or more elements, then it has to divide one of them. So if it divides this product here, then it has to divide one of these QIs. So maybe it has to divide, let's say, some QJ here, right? So this P1 will have to divide QJ for some for some J. But QJ is also prime. So therefore, that will mean that P1 and QJ are essentially equal, up to maybe plus or minus sign in case of integers. Sorry, in case of integers, in fact, primes are positive, never mind. So it's always plus. In the case of polynomial ring also, never mind. So here also for polynomials also, I assume that the leading coefficient is 1. So in fact, I don't need this part here. When I wrote, I was not thinking like that. So in fact, QJ will have to be exactly equal to P1. And what that means is that therefore I can actually cancel off. I can divide both sides by P1 and QJ. And then I'm left with a smaller number. And of course, this will become N over P1. And then I'm left with a smaller number. I'm left with a smaller number. So I inductively proceed. And then I can see that uniqueness holds, that this factorization on this side will have to be same as the factorization on this side, because I am now dealing with a lesser number of factors. So I'm not going through it formally, but that's basically the proof that you see that there is a common prime occurring on both sides. You cancel it off, and now you are dealing with less number of primes. And so proceed by induction, and you will see that both sides have the same number of primes and the same set of primes. So the prime factorization is unique. And all that really comes down to knowing this particular property. This is called as a prime property. I hope this part of the proof is clear to everyone. So to prove the uniqueness part in these theorems, I need to establish the prime property, and then I'm done. So now that is what I'll do. I'll try to explain what this, how one goes about doing the prime property. So the prime property is proved as follows. Basically, it starts off with Euclidean. So, okay, first let's start with the Euclidean algorithm for computing the GCD of two elements. And again, I'm giving examples from integers, but you can also put polynomials here. So I will briefly say what will that involve. So here also everything could have been polynomials, and it's the same argument. Wherever you see prime, you just put an irreducible polynomial, and otherwise the same argument everywhere. So the Euclidean algorithm for computing GCD of two elements. So GCD is the greatest common divisor. So for example, 253 is one number here, and 161 is the other number. I want a divisor. I want the greatest common divisor, which means I want a number which divides both of them, and which is the largest among all the numbers which divide them. And the Euclidean algorithm, so sometimes it's covered in school, sometimes it's not. So let me just quickly go over it. What does it say? It's you look at 253 and you divide it by 161. And so I take 253 divided by 161, and the remainder is 92. Then the GCD of 253 and 161, these two numbers, is also the same as GCD of 161 and 92. So I can replace this bigger number by this smaller number. I replace this thing that I'm trying to divide by the remainder. And that's because anything which divides both these will also divide this. And anything which divides 253 and 161 will also divide 92 because it's just the difference. So might as well look at GCD of 161 and 92. And now you repeat the process. So 161 is 1 times 92 plus the remainder, which is 69. 92 is 1 times 69 plus the remainder, which is 23. And 69 is 3 times 23 plus the remainder, which is 0. So once you hit the 0 remainder, that means that you have found the GCD in the previous step, and the GCD is 23. So this is a very simple process, and it goes back to Euclid in some form or the other. And so therefore, we have a simple algorithm for computing the GCD of two elements. Just use this division with remainder all the time. And since division with remainder also works for polynomials, you can have two polynomials here, and you can try to repeat the same process. Simply check, divide this polynomial by this one, and the remainder should either be 0 or should have smaller size, which means the degree. In the case of polynomial, you use the size as degree. So it should have smaller degree than the degree of what you are dividing by. You are dividing by 161 in this case, so it should be smaller than that. So in general, whatever polynomial you are dividing by, if you are using polynomials here, then this should have smaller degree than this one. And then you repeat the same process. So for polynomials also, you repeat the same process till you hit 0. And then the previous step, whatever you get, will be the GCD of the two polynomials. So that is the Euclidean algorithm. Yes?
This answer is a question in the chat. So
yeah.
If you
what is the question? Can you read out the question? Yeah.
Hello.
Yeah. Please go ahead.
Yes, sir. So my doubt is, I understood the process, the algorithm, but my question is, how does this lead us to the GCD? Like how and why, the logic behind it, I'm not getting it.
Yeah, that's because, okay, look at it, this situation, the GCD of 253 and 161, any divisor which divides 253 and 161 should also divide 92. And any number which divides 161 and 92 also divides 253. So the GCD of, so let me write it here. This is the same as GCD of 161 and 92. Just from the first sentence, what the first sentence is showing you is that the GCD of 253 and 161 is the same as GCD of 161 and 92. Do you agree with that?
Yes, sir. Yes, sir.
Yeah. And now you just repeat. Now repeat this. Now the GCD of 161 and 92 is the same as GCD of 92 and 69. And so just keep on continuing like this. GCD of 92 and 60. So this is the same as GCD of 92 and 69 and ... So
okay,
in the end, you will get GCD of 69 and 23, but GCD of 69 and 23 is 23 because 23 divides it.
Okay, understood, sir.
Yeah.
Yes.
All right. So this is the Euclidean algorithm for computing the GCD. But there's a nice thing to it, which is that it also tells you how to write the GCD as a linear combination of the two numbers that you started with. So I started with 253 and 161. I will now say that 23 is a linear combination of 253 and 161. So for that, I will go backwards from here. So I know 23, I will write it as a linear combination of 92 and 69. And that I already have here. So that's what it is. 92 minus 1 times 69. Next, I know 69 is a linear combination of 161 and 1 times 92. So what I'll do is I will substitute for 69. I will substitute 161 minus 1 times 92. So when I do that and I reorganize the coefficients, I will get 161 because there's minus and minus. So I'll get, sorry, something went wrong. 69 is 160. Oh, sorry, it's minus. Ah, never mind. So this was a minus, there was a minus here. So what I see is that I get minus 161 plus 2 times 92. When I rearrange the coefficients, I substitute 69 is equal to 161 minus 1 times 92. I got that relation from the second line. And then I go backwards, first line. In this, I look at 92, and 92, I can express it as a linear combination of 253 and 161. So 92, I will write it as a linear combination of 253 minus 1 times 161. Okay. And so therefore that will tell me, then I rearrange the coefficients and I get 2 times 253 minus 3 times 161. So I hope this process is clear. And what it is doing is it's telling me that 23 is 2 times 253 minus 3 times 161, just by going backwards. Right? This as a linear combination of these two, then use the fact that this guy here, 69, is occurring here, and this is a linear combination of these two. Then use the fact that 92 is occurring here, and 92 is a linear combination of these two. So just go backwards, and you get 23 as a linear combination of 253 and 161. And again, you can do this for polynomials also. It's the same process, because all I'm using is addition and multiplication, and I'm just going backwards. So if I had polynomials in all these places, then you use polynomials here. Here, instead of numbers, again, you will have polynomials as coefficients, and you will write your GCD polynomial as a linear combination of the original two polynomials you started with. Same process, no difference. Okay. And so what I get is that if I have this is the thing that this is very important, that I've gotten the GCD as a linear combination of the two elements. And now I'll use this fact to prove the prime property. The prime property is right here. P divides M1, M2 implies P divides M1 or P divides M2. So let's prove that. So suppose P is a prime element. Suppose P is a prime number in case of integers, or maybe an irreducible polynomial in case of polynomials, the set of all polynomials. So suppose P divides M1, M2, and P does not divide M1. Then we want to prove that P divides M2. So P does not divide M1. We want to prove P divides M2. So first thing is, if P doesn't divide M1, then by definition, because P has no other prime other factors, the GCD of P and M1 has to be 1. And because the GCD, so note here that I am defining the GCD without using the prime factorization. GCD is basically the largest element which divides both of them. And since there is nothing which divides P other than itself and 1, so therefore the largest, the only integer, in case of integers, the only thing that divides both P and M1 is 1. In case of polynomials, you can say that again, only constants divide both of them, and by default, I can take the constant to be 1. And you can then use again the same thing. So GCD of P and M1 will be 1. So there will be, if these are integers, then there will be integers A and B in Z. And if these are polynomials, then there will be polynomials A and B in f of x, such that AP plus BM1 is 1. That comes from this Euclidean algorithm and what we said here, right here, that you can write the GCD as a linear combination. So 1 is the GCD, so 1 you can write it as a linear combination. So I'll get some coefficients A and B such that AP plus BM1 is 1. And now multiply both of them, both sides by M2. So AP M2 plus BM1 M2 is M2. But notice there's a P here, and P divides M1 M2. That was our basic hypothesis here. So P divides both these terms. So therefore P divides M2, which is what we wanted to prove. So is this part clear to everyone? So we have therefore given a proof of why uniqueness of factorization holds. And the crucial thing was to get this prime property. And the prime property in particular depends on getting the GCD as a linear combination of two elements, which in turn really depends on the Euclidean algorithm. So in the end, we seem to be relying on the Euclidean algorithm. And after that, we can sort of get other things going just mechanically. This is what I'm now going to exploit in what is going to appear next. Okay, so shall I move on?
Yes, so far so good.
Okay, so before we go ahead, let me make an observation. We looked at all these polynomials over R, Q, and reals, complex, and rational numbers. So it would also be useful to know what are the prime elements, what are the irreducible elements. And the irreducible elements in CX, so this is a theorem. Again, if you are used to dealing with complex numbers, you sort of get used to using this fact also without proof, is that every irreducible polynomial is linear, meaning that, of course, whenever I talk about irreducible polynomials, I'll always assume they are non-constant. And so, in fact, they turn out to be of degree exactly 1. And that's equivalent to saying that every polynomial has a root. Every non-constant polynomial has a root. And that's because you can factor these polynomials and you can bring them into irreducibles, but the irreducibles ones are linear. But what does a linear polynomial look like? It looks like some ax plus b. And in fact, if you get rid of the a factor, then it's like x minus x plus some constant. And so that's a root, or minus of that constant is a root. So therefore, since any non-constant polynomial can be factored into linear ones, and linear ones really correspond to the roots, so every non-constant polynomial has a root. And so this second part of the sentence is sort of equivalent to the first part, which says that every irreducible polynomial has degree exactly 1. Whereas over real numbers, you can get almost close to that, but we know that x squared plus 1, for example, is an irreducible polynomial which doesn't have real roots. So the best thing you have is every irreducible polynomial has degree at most 2. So it can be degree 1 or degree 2. And so this is a side remark I will make. I'll come back to this remark at the end of the lecture. So in particular, any polynomial or rational function over C is essentially determined by its zeros, because a polynomial over C is completely determined by, I mean, I say almost completely because there's a constant hanging around always. But otherwise, a polynomial is basically described by the zeros of its polynomials, its roots, basically. And if you have a rational function, then it's a ratio of 2 polynomials. So there is zeros and infinities, which are sort of things appearing in the denominator, the roots of the denominator. That's where the function seems to go to infinity. So anyway, this is, I'll leave this infinity part right now. Let's move on. So now the next question is, where else can we have this unique factorization property? So we'll now try a new set. So this is a set which you may or may not have encountered, I mean, in this particular form in your school days. So for example, this is the set Zi, where I is again square root of -1. So this is basically all, this notation is a general notation, and what it means is I'm looking at all polynomial expressions in whatever is inside the bracket with coefficients coming from Z. So it means that I'm looking at all expressions of this form. But in case of I, we already know that I square is -1, which is an integer. So in fact, you can absorb this one with this here. And similarly, I cube is minus I, so you can absorb the cube term with I here. So basically, all the higher powers can be absorbed in the first two terms, and so therefore we can simply write it as A plus BI. But in general, if instead of I, if I put something complicated here, then this is the general definition. Okay, so that's why I first gave the general definition, and fortunately in this case it's actually much simpler. It's just A plus BI. So these are all the complex integers, and they are also called Gaussian integers in honor of Gauss. I hope you have all heard about this mathematician named Gauss, who gave fundamental contributions to many areas of mathematics. So here's a theorem. The theorem says that over Zi also you have unique factorization. So again, I should first mention this in the side. What are all the multiplicatively invertible elements? Means those whose reciprocal is also in Zi. What are all those complex integers whose reciprocal is also a complex integer like this? And it is not hard to see that these four are the only ones. I mean, if you have a non-zero coefficient in both of them, then the reciprocal will not have integer terms. You can easily check that. And so therefore, one of them has to be 0, and then it's easy to also to check that it has to be plus or minus 1. So these are the only complex integers whose reciprocal is also a complex integer. Okay, so the theorem is that unique factorization also holds in this set, in this collection. And so every element here, oops, I meant to say non-zero. So let's just say that, because 0 is an unnecessarily, I mean, 0, you have infinitely many factorizations or whatever. So every non-zero alpha factors as pi 1. Now I'm just using Greek letters just for the heck of it. So as a product of these elements of Zi, pi I, so pi 1, pi 2, pi 3, pi k, like that, where these pi j's are irreducible elements in Zi. So they are like prime numbers, they are irreducible elements, which means you cannot factor them further, which means that if you do factor them, then one of them will have to be a unit like this. It has to be plus or minus 1 and plus or minus I. So, multiplying by plus or minus 1 or plus or minus I should not really be considered serious as far as factorization is concerned. So therefore, we want to ignore that kind of factorization, and therefore ignoring that, then pi j's are irreducible. So those are they are non-units. That means they are non-invertible, which cannot be factored further. And moreover, the uniqueness.
Sir?
Yeah.
There are a few requests to go over what Gaussian integers are again.
I have said here, no, Gaussian integer is all a plus bi, where a and b are in Z. This is Gaussian integers.
And complex reciprocals.
They are the same. So Gaussian integers and complex integers are the same. Is equal to
units. Units in Z.
Sorry?
The units in ZI, there was one confusion.
Units in ZI. Units are, as I said, again, they are invertible elements. So elements whose reciprocal, whose multiplicative inverse is also a Gaussian integer. So I claim that the units are plus or minus 1 or plus or minus I. So I think I'll leave it as an exercise for you. So what I'm saying is that if 1 plus a plus bi also belongs to Zi, implies okay, whatever, I don't want to write that, so I'm sorry. That implies that's the property. So unit means this is the property I'm interested in. So a plus bi, such that 1 plus a plus bi also has integer coefficients, and I leave it to you as an exercise to check that they are just 4 of these. Okay, so I'll go on. Let me finish this theorem that every alpha factors as a product, and moreover, these irreducible elements are unique up to multiplication by a unit. You will see by some examples. Maybe I can go down and give you some examples. Basically, if I say that something is irreducible, you can multiply it by -1, and you can say that is also irreducible. I mean, in some sense, multiplication by -1 doesn't count as far as factorization is concerned. And similarly, you can multiply by I, and that's a reversible process because you can multiply by -I and you can get back your original number. So multiplication by plus or minus 1 or plus or minus I is not important as far as factorizations are concerned. So these are the only elements whose multiplicative inverse, means reciprocal, is also in Gaussian integers. The reciprocal of I is -I. So pi j's are unique up to multiplication by one of these elements. So that is the uniqueness part here. So every element can be factored, and moreover, each factor is almost unique. It's unique up to multiplication by plus or minus 1 and plus or minus I. And so I'm going to now sketch a proof of this, and I'm also going to sketch one application of this. So we have gone into some new collection of numbers or new situation wherein we are looking at this set Zi, which is the Gaussian integers, or it's the same as complex integers. So I'm looking at the complex integers here. I mean, these two are equal. So the proof again is a similar strategy as before. We are going to basically use the Euclidean division method to compute the GCD, and then everything else follows as before. So to do the Euclidean division, basically, let's go back here. And what does the Euclidean division involve? Given two numbers, 253 and 161, what you have to do is take this number, divide it by this number. And there'll be a quotient, and there'll be a remainder. And the remainder should be either 0 or should have size smaller than what you're dividing by. So remainder 92 is, well, in this case, it's not 0, but it's important to note that it's smaller than 161. And at every step, the remainder was smaller than what you're dividing by, the divisor. So that's what I want to do here. Take a number, take two complex integers, alpha and beta. I want to divide alpha by beta. And if I do that, then I want to find the quotient and the remainder. And the important property is that in this case, to estimate the size of R, I am going to use mod R square, or for any alpha, I'm going to use mod alpha square as the size as the size of any, so forget the word function here, as the n-valued size. Let's just say size. This might confuse some people. So the size of any alpha, for the division process, I need to estimate that this remainder is smaller than the divisor. And for that, I should have smaller in what sense? So I will say that I will use the size. For the size, I will use absolute value square, mod of alpha square as the notion of size. So in this case, that would mean, so if you can ignore this sentence if you like, all I'm asking is, given two complex integers, can we find a quotient and a remainder such that alpha is q beta plus r, and the remainder satisfies r square is less than beta square, mod r square is less than mod beta square. If I can do that for in every situation, then I can repeat the Euclidean division algorithm, and I mean, not just division, this GCD algorithm. I can repeat this GCD algorithm, and I can actually compute the GCD of two complex integers also. So that is what now I'm going to explain why it happens. And this is a more geometric idea. I mean, or at least it's nicely seen if you visualize it geometrically. So I hope it's clear to everyone what I'm trying to do. So I'm trying to divide alpha by beta, and alpha and beta are complex integers. So what I've done here is I've drawn various complex integers. These are my complex integers. So this is 1, this is 2, 3, this is I, 2i, 3i, and minus 1, minus I, minus 2i, minus 1, minus 2, etc. So let's take an arbitrary beta. So here's I've just taken beta. In this case, beta is, let's see, 1, 2, 3, 4, 5 plus 2i. So in this case, beta is actually 5 plus 2i. And so if you look at, this is beta, if you look at I beta, that will be rotation by 90 degrees, and you will basically get 5i minus 2. So this is minus 2 plus 5i. And so 5i here, oh, I hope it's correct, 1, 2, 3, 4, 5. Yeah, so this is I beta. And minus beta is right here. So that's another multiplication by I. And the third multiplication by I will bring it here, which is minus I beta. And the fourth multiplication by I will bring it back here. So these are the basic multiples. And you can see that this is, again, a complex multiple of beta, complex integral multiple of beta. This is beta plus I beta. So which is 1 plus I times beta. And similarly, this is minus 1 minus I beta. So if you look at all the complex integral multiples of beta, basically you will be constructing this bigger lattice. You'll be constructing this big lattice, squares like this, which have size length beta, mod beta. Each side has length mod beta. So that's a square I've drawn here. And alpha is what I'm trying to divide by beta, will be located in one of these squares, somewhere in the plane, somewhere in the complex plane. Alpha is sitting somewhere. So one of these squares will contain alpha, and that square I've drawn here. So this is a square in which the vertices are all complex multiples, complex integral multiples of beta. Beta, I beta, 1 plus I times beta, 1 minus I times beta, and so on and so forth. So 2 beta will be here, 2 plus I beta will be here, etc. So the whole plane is covered by squares like this, various squares like this, and one of those squares will contain alpha. And the vertices of these squares are my complex multiples, integral multiples of beta. And so now the question is, how do I express alpha as some complex integral multiple of beta plus a remainder? Well, the picture is telling you how. This is your square. Inside the square, alpha is located. What you can see is that the distance, the closest point to any point to alpha will always be less than the length of beta. And therefore, this is your remainder term. And this will be, so this will be your q beta. And this, the complex number obtained by drawing the arrow from here to here, meaning the difference between q beta and alpha, this is your r. This is your remainder. So your remainder is q beta minus alpha. Maybe your origin is somewhere here or somewhere here. I don't know, wherever it is, wherever your alpha is. And so q beta minus alpha is this distance. So is this complex number. So this complex number is alpha minus q beta, and that is your r here. And you can see that R has length smaller than beta. The closest point to alpha will always have length smaller than beta, unless alpha is one of the vertices, in which case R is 0. So I should probably add or R is 0. Okay. So therefore, this is how the division algorithm works for complex integers. And once you have the division algorithm for complex integers, now you just repeat this process. If you want to compute the GCD of alpha and beta, you divide alpha by beta and you get this. Now the next step, you will take beta and divide beta by gamma. Not gamma. This okay. This does look like gamma. Never mind. This I meant it to write it as R, but okay, you can think of it as gamma also. Whatever. So beta you can divide by R, and that will be your next division. Next division. And so you keep repeating the same Euclidean algorithm. You just follow the Euclidean algorithm till you hit a 0, and then the previous number that you obtain will be the GCD of alpha and beta. So computing the GCD of alpha and beta follows the same procedure as before. Once you have that, then you can again express the GCD of alpha and beta as a linear combination of alpha and beta. Once you have that, then you can prove the prime property. Once you have the prime property, then you can prove uniqueness of prime factorization. I forgot to mention why you can factor it into irreducibles in the first place. And that's again same as before. Take a complex integer. Only thing is use the size as this is integer valued size function, and see if you can factor it as a product of smaller complex number integers. If you cannot, then it is an irreducible element. Otherwise, you will break it up into two smaller complex integers, and they will all have smaller natural number valued size. And so therefore, this process has to stop after finitely many steps. So you can always factor, never mind, you can always factor it as a product of irreducible elements. And the uniqueness is it requires a little bit of effort, and that uniqueness follows because you have the Euclidean division. That's all you need. That's the point I'm trying to say. That you have, once you have Euclidean division, then uniqueness follows. That's because once you have Euclidean division, you can in fact compute the GCD. Once you have computed GCD by this process, then you can in fact write the GCD as a linear combination. From that you get the prime property, and from that you get uniqueness. Same arguments as before. All right. So yeah, I mean, I've left some steps here, but I leave it to you to check that the same proof works as before. It's just mechanical. I mean, whatever, once you write down the previous proof, then it's absolutely the same proof. There is no difference. And in fact, you can argue abstractly all of them together in a uniform way. And then the next question is just like for the case of polynomials, what are the prime elements now? I mean, what are the irreducible? Prime means irreducible here. Prime and irreducible are the same things here. So what are the irreducible elements here? And in complex integers. And moreover, which prime numbers in Z also, because prime numbers in Z are maybe suitable candidates for primes in Zi, because I mean, I don't know otherwise how to get started with primes in Zi. So the first thing is to make a guess. Okay, let's take a prime in Z, and we can ask whether it splits in Zi, whether you can factor it in Zi further. So the question is, which primes can be factored further in Zi? So I have already written a few cases here. You can try this out. So 2, for example, you can factor it as 1 plus I times 1 minus I. Neither of these is an invertible element. I mean, they are not units. 3, however, you can try, and you will see that you will have to, I mean, you will not be able to factor it. And similarly, if you try with 5, you can see you can write it as 2 plus I times 2 minus I. In fact, you can also write it as 1 plus 2I times 1 minus 2I. And so this, before we move ahead, this gives me the question, does this violate unique factorization? I said above that I can factor any number uniquely. So I have written it as 2 plus I times 2 minus I, but here I'm also telling you it is 1 plus 2I times 1 minus 2I. Do you see a problem there? Anybody? Do I really have 2 different ways of factoring 5?
The answer is saying it's one and the same. Maybe I'll let you elaborate. I'll just allow you to.
Yeah, they are one and the same because you can multiply one of them by I and you'll get the other one. So you multiply this by I or maybe minus I. So let's multiply this by I. Then if you multiply this by I, then you get 1 plus 2I. And if you multiply this by minus I, you'll get 1 minus 2I. So actually they are the same factorizations, just the invertible factor of I has been moved around. That's all. Okay, and similarly, you see that 7 cannot be factored, but 13 can be factored, 11 cannot be factored, 17 can be factored, 19 cannot be factored. So what is the pattern here? I mean, okay, this is special because this is an even prime. The odd primes here and there are odd primes here. So what is the pattern here? I hope all of you can see what the pattern is occurring here. And in fact, the answer is there on your screen. It's a theorem. I'm not going to prove it. It's not difficult to prove. Take a prime integer and suppose it's of the form 4k plus 3, like these, then it remains irreducible in Zi. It will not split in Zi. On the other hand, if it's of the form 4k plus 1, like 5, 13, 17, then it will split in Zi. And moreover, the moment you split it, those factors will be irreducible. So all these 1 plus I, 2 plus I, 2 minus I, 3 plus 2I, 3 minus 2I, 4 plus I, 4 minus I, they are all irreducible in Zi. And in fact, these are the only irreducible elements in Zi. The only irreducible, all the irreducible elements in Zi are obtained by this process only. So they are basically 3, 7, 11, 19, 2 plus I, 1 plus I, 3 plus 2I, 4 plus I, and the conjugates. So these are the only irreducible elements. There are no further irreducible elements in Zi. So this is an interesting theorem. It's not difficult, but it will be too much for me to cover this also in this lecture. So I'll skip this part. But let me now sketch an application of this. As an application, what you see is that any integer n. So now this is an application to ordinary integers. So we analyze this new collection of complex integers, but we in fact get a benefit of getting a result for ordinary integers. Any integer n greater than 0 is a sum of two squares, meaning you can write it as n is equal to a square plus b square, if and only if in the prime factorization of n in Z, every prime of the form 4k plus 3 occurs an even number of times. Yeah, every prime of this form occurs even number of times. Whereas 4k plus 1 kind of prime can occur as many times as you want, but 4k plus 3, that prime should only occur even number of times. So I will not prove this consequence also, but I'll just illustrate it by our two examples. So here are the two examples. 65 square, for example, is 5 square times 13 square. These are both of the type 4k plus 1. So this is 2 plus I whole square, 2 minus I whole square. This is 3 plus 2I whole square, 3 minus 2I whole square. And I want to write 65 square as a sum of two squares, which means I want to write it as a square plus b square. But what is a square plus b square? A square plus b square is a plus ib times its conjugate. So I want to write this whole thing as a product of one complex number followed by its conjugate, which means I should just rearrange these prime factors. And how do I rearrange these prime factors? So that one half comes here and the other half is in the conjugates. That's how. So for any prime factor, its conjugate should not be, conjugate should occur on the other side. So then if you think, try it out, you can see that these are the possibilities. So let me just go over one or two of them. So first one is 2 plus I whole square and 3 plus 2I whole square I put, and the remaining are the conjugates. So that's 2 minus I whole square, 3 minus 2I whole square. Similarly here, similarly you can do this. And then I decided to take 1 2 plus I and 1 2 minus I. So that gives me 5. Then the conjugate is 2 minus I and 2 plus I. So that 5 again has to appear here. And this side I took 3 plus 2I whole square. And then the conjugate is 3 minus 2I whole squared. So that is this one. So you have these 5 cases. And if you expand this out, this will turn out to be 33 plus 56i. And this will be 33 minus 56i because this is just the conjugate of this. So it gives you 33 square plus 56 square. So similarly, if you work out these calculations, you'll get these squares. And these are the different ways. So we have also enlisted the different ways in which 65 square can be expressed as a sum of two squares. So we in fact get that also. On the other hand, if I had added one extra factor of 3, then this condition is violated. 3 is a prime of the form 4k plus 3, but it is not occurring even number of times, it's occurring odd number of times. Then notice what happens. So then there is 3 times pi square times 13 square, and I want to write it as a plus ib times a minus ib, because I want to write it as a sum of 2 squares. But then 3 is a prime element in the Gaussian integers. So 3 will definitely, if it divides a plus ib and a minus ib, by the prime property, it has to divide at least one of them. So let's say 3 divides a plus ib. But if 3 divides a plus ib, then 3 will also divide a minus ib, because you just conjugate it. The conjugate of 3 by conjugation will divide a minus ib. If 3 divides a plus ib, the conjugate of 3 will divide a minus ib. But of course, the conjugate of 3 is 3 itself. So this means that 3 will also divide a minus ib. That means that 3 will have to appear 2 times on this side, but this side is appearing only once. And that's a contradiction. I hope that part is clear to you. So therefore, if 3 occurs once, there's a problem. So if a prime like 3, it has to occur twice or 4 times, meaning even number of times, if you want to write it as a sum of squares. So that's a nice consequence of our thing. So like that, we are now tempted to ask whether we can do unique factorization in other situations, because then we can get nice applications like this. And indeed, you can, it does happen to be true in other situations also. And so you do get a few applications. This is probably the simplest and the nicest. But still, one could ask this question. And it turns out that unique factorization doesn't always work. So now I will concentrate on situations where unique factorization doesn't work. Okay. So here are some examples where it doesn't work, and I've also written down why it is not working. You have to check a little bit in each case. So for example, in z root minus 3, you can see that 1 plus root minus 3 into 1 minus root minus 3 is 2 times 2. What you have to check is that these are irreducible in this set. I mean, in this collection of integers, or in this collection of numbers, you cannot factor this further here. So you have to check that. Similarly, 2 also you cannot factor. It's not hard to prove, but you still have to do a little bit of checking. So since there's not much time, I will not go over it, but it's not hard to prove that. Similarly, in z root minus 5, you can see that 1 plus root minus 5 into 1 minus root minus 5 is 2 times 3. And all these are irreducible elements. They cannot be factored. And similarly here, I have switched over to polynomials. So you take polynomial x and then adjoin some, again, here I am adjoining some square roots. So here also I am tempted to adjoin some square roots. So I adjoin square root of x cubed. And immediately you see that unique factorization is failing here. Again, you have to check that you cannot factor x to the power 3 by 2 in this collection, or x is cannot be factored in this collection. This collection, by the way, means that all polynomial expressions in x and x to the power 3 by 2. With coefficients in f. F can be complex, real, or rational, or pretty much, I mean, there are other possibilities also, but let's not get into that. So similarly here, f x square root x into x plus 1 into x minus 1. And if you call this quantity as y, then you can see that unique factorization is failing, because y times y is x into x plus 1 into x minus 1. Okay, so what it turns out, and I won't spend time on this, is that in these two situations, actually, there is a simple remedy. And there's a simple explanation for why unique factorization is not holding. And that's because these sets were deficient in the number of, oops, did I? Yeah, these, sorry, my hand went somewhere, so it jumped. So these sets are deficient in the number of elements they contain. And for example, in this particular situation, you have this element omega. This is the cube root of unity, which is obtained by just taking a fraction from this set. You take a fraction in this set, namely minus 1 plus root minus 3 by 2. So it's almost here. It's a fraction. But this element omega is also a nice integer type element because it satisfies an integer like polynomial. It satisfies a polynomial of the it's a root of a polynomial. Never mind. So this is a root of x cube minus 1. Well, let me write it as to be uniform. Right. Okay. Let me just say x cube minus 1. So it's a root of x cube minus 1. This element is a root of x cube minus 1. The important property here is that the coefficient in front of x cube is 1. And that is useful because just look at integers versus rationals, integers versus rational numbers. You will see that integers satisfy any integer. Suppose I give you an integer n here, it satisfies the polynomial x minus n is equal to 0. But if suppose I give you a over b here, the integer valued polynomial, integer coefficient polynomial satisfied by a by b is bx minus a. So the difference between looking at an integer and looking at a rational number with non-trivial denominator not 1, is that the smallest degree polynomial satisfied by this with coefficients in integers is this, whereas smallest degree polynomial satisfied by this with coefficients in integers is this, and that has a has some coefficient not equal to 1 in front. So these are non-integer type elements, and this is an integer type element. So that is a small subtle technical thing. I won't emphasize too much on this. So the point is that omega is an integer type element because the polynomial it satisfies has coefficient 1 in front. Integer coefficient polynomial it satisfies has coefficient 1 in front. So that is why it's an integer type element, and that integer type element was missing here. So you can look at this collection, and in this collection one can show that unique factorization holds. So anyway, this is a slightly technical point. I don't want to emphasize too much on this. So therefore, all I'm trying to say is that in this case, we were looking at a deficient class of integers, integer-like elements, and that's why unique factorization was failing. If you concentrate on this collection, then actually you can do you can get unique factorization, because in fact you can work out Euclidean division algorithm by using absolute value square. But in contrast, no such luck with this situation. So this is the new situation, and for the last 5-10 minutes I will now talk about this situation. So this is a situation where we are not able to fix this, no matter what elements you take. Even if you take elements like 1 plus root minus 5 by 2 or some such thing, if you try to take an analogy, they will not satisfy a nice polynomial like this which has coefficient 1 in front and other coefficients as integers. So they will not satisfy an integral polynomial with coefficient 1 in front. Those are called monic polynomials. So they will not satisfy such polynomials. All the elements here which satisfy those polynomials are already here. So looking at fractions here will not give you anything, and will not give you anything better. So it turns out that unique factorization here is failing for a much deeper reason. And similarly here also. In this case, again, if you take the ratio, if you look at the ratio of these two, you get x to the power 1 by 2. And look, I mean, here I obtained this from the original polynomial ring by attaching square root of x cube. But I'm saying there is already another square root present there, which is square root of x. And I could have attached that also. So that was a deficient thing in this ring, this collection. And therefore, I was not able to get unique factorization here. But if you look at this collection, I get unique factorization here because I can think of this as a new variable, and then I get this is like a collection of all polynomials. So here I have unique factorization, here I have unique factorization. And so I can somehow say that this situation can be understood by saying that actually the unique factorization was happening here, and then here I had missing some elements. But in these two situations, that doesn't happen. Okay. So what I will now do is I will, for the last 5-10 minutes, I will try to explain what is the remedy for this kind of situations. Okay. So to the organizers, yeah, go ahead.
I'll just ask them to unmute.
Sorry. Yeah.
Hello.
Yes.
Sir, I have a doubt that above you had told us that 4k plus 3 terms are not reducible in complex.
Yes.
But my doubt is, like, 4k plus 3, we lead it like 4k. 15 is also a form of 4k plus 3.
No,
and
no,
we-
no. Yeah, yeah. Okay.
So if, since 15 is like factorizable in the real plane, it has to be factorizable or reducible in the complex one.
Okay. So first of all, I'm only interested in primes. Let P be a prime in Z. So 15 is not a prime.
Okay, okay. So 4k plus 3 types primes you are referring.
Primes, yes, yes. Primes in Z, which are of the type 4k plus 3.
Okay, understood, understood.
Yeah.
And one more doubt, like why
Yeah.
is representing a prime number in the terms of two squares or product of two squares unique?
No,
Yeah,
it's not
or-
unique. For primes. Yeah, primes, it will turn out to be unique. No, that is a consequence of this theorem. I mean, it needs a proof. I have not explained why, that it comes from the proof.
Okay, okay, sure. Understood. Thank you.
Yeah. Okay, so to the organizers, can I just use another 5-10 minutes?
Yeah.
Okay, thanks. So now I will concentrate on situations where unique factorization does not work. Okay, and so unique factorization will not work. There are many situations, but just forget this part. There are situations where the explanation is slightly different. You can it's because the collection of integer-like elements that you are, or whatever collection of objects that you are looking at, of elements that you are looking at, they were deficient in some ways. So, but there are situations where that by itself will not account for why unique factorization doesn't hold, and then it turns out that there is still a remedy, and you can actually recover unique factorization in this also. But for that, you have to work slightly differently. And that idea actually is interesting. So I will now concentrate on that. So it goes like this. So this is going to be slightly abstract, but I hope you can follow. So what we'll do is, instead of working with individual numbers or individual functions in this setup or in this setup, we will work with a large collection. So we'll work with what are called as ideal numbers, or in fact, the abstract word nowadays people use is just ideals. So this is a better word because I want to apply it in different situations where things are not necessarily numbers. Here they are functions. So I'll just call them ideals. So we work with large collections called ideals, and they are defined in the following way. This will be a large collection. Okay, this will be an infinite collection, in fact. So fix some elements in your set and look at all linear combinations of these elements. So C1, so if A1 to AN are fixed, look at C1A1 plus C2A2 plus CNAN, where CIs are varying. So CIs are varying, only A1 to AN are fixed. Look at this entire collection. I will call that as the ideal generated by A1 to AN. So this is one ideal. So I look at various such ideals. By varying my N and varying A1 to AN, I get different ideals. Meaning for a particular ideal, I have to fix the fix A1 to AN. So for a particular ideal, I have to fix this this collection, and I have to look at all possible linear combinations of these. So the final ideal is actually this set. The set is this. The notation for that ideal is A1 to AN, like this. But the underlying set is all linear combinations of A1 to AN. So let me show you by an example. So for example, in Z, I want to look at the ideal generated by 6 and 10. So N is 2, A1 is 6, and A2 is 10. So if you look at all linear combinations of 6 and 10, we know from the Euclidean division process that the GCD2 is also a linear combination. In fact, you can see that 12, which is 2 times 6 minus 10 is 2. So there is a linear combination which will give me 2. And so therefore, if I look at all possible linear combinations of 6 and 10, I will get all possible even numbers. I'll get every even number. I won't miss out a single one. So 6, all linear combinations of 6 and 10 is the same as all even numbers. And so similarly, I will leave it to you to check that if I give you some n integers in Z, and I look at all linear combinations of A1 to AN, that's the same as all multiples of the GCD. So this infinite collection will be an ideal. But what we see from here is that the ideals in integers are not really new things. They are just these. They are all generated by one element. I mean, even if you start with n elements, finally you can replace them by just a GCD, and they are just generated by one element. So for example, I could have looked at this ideal, but this ideal is the same as just all even numbers. So the set of all ideals in things like Z is just all multiples of one particular element. And so it's almost the same as looking at this number which is generating it. And so therefore ideals in Z are not really different from, are not that different from looking at numbers in Z, just looking at a single one particular integer in Z. It's not really that different, up to plus or minus sign. It's you could 2Z is also the same as minus 2Z. So up to a minus sign, plus or minus sign, it's the same thing. So ideals in Z are just of the form dz. So ideals are not really different when it comes to looking at Z. Similarly, for polynomial ring fx, same thing. You will see that an ideal in fx is again generated by one polynomial. So they are not really giving anything new whenever the Euclidean division process works. But in situations like these, where the Euclidean division process doesn't work, it turns out ideals are something interesting. So here are the facts which will help you appreciate what is happening. So let A is equal to Z root minus 5. And I look at all linear combinations of these two elements, 1 plus root minus 5 and 2, with coefficients from A. So I look at this infinite collection. Now, if I were dealing with integers, I would have just said, well, this is the same as looking at the GCD and looking at all multiples of the GCD. So in this case, I'm sort of trying to get the GCD of 2 and 1 plus root minus 5, but they have no common factor. So the GCD should be 1, but in fact, I will not get 1 here. So I will not get 1 as a linear combination. I will get one big infinite collection here. I mean, but that infinite collection will not contain the element 1. So it will miss out at least something. So this, I'll get one big infinite collection here. Similarly, look at all linear combinations of 1 plus root minus 5 and 3. That is another big infinite collection here. Here's the third one, 1 minus root minus 5 and 2. Look at all linear combinations. In fact, this is just the conjugate of this. In fact, you can also see that I and I bar are the same, because 2 minus 1 plus root minus 5 is 1 minus root minus 5. So you can see that linear combination of these two will contain 1 minus root minus 5, and linear combination of these two contains this. So in fact, these two are the same sets. And the conjugate of this set, meaning look at conjugate of every element of this set, that will be 1 minus root minus 5 comma 3a. And so the interesting fact is that product of, you multiply all the elements here with all the elements here, that is ij, okay, and add them up. So, okay, this notation needs a little bit more explanation. Sorry about that. So this is actually sums of products of all elements from here to here. I am a bit sloppy here. Sorry, I'm running out of time. So let me just orally say it. So I look at sums and products of all the terms from here and here. That is my ij. So it turns out that this product will give me 1 plus root minus 5. This product will give me 1 minus root minus 5. This I bar will give me 2, and all multiples of 2. And if I multiply every element of j and every element of j bar, I multiply and add them up, then this will give me 3, all multiples of 3. So why am I saying this? Basically, this turns out, it explains the, it gives you a new way of looking at unique factorization. The reason why 6 was, see, this was 6 here. The reason why this 6 was being written in 2 different ways was that each one of all these terms here were themselves not actually irreducible. They were actually, I mean, they are irreducible here, but in fact, what is going on is that if you look at the ideal generated by this, or the ideal generated by this, or the ideal generated by 2, or the ideal generated by 3, those ideals are not irreducible. And they split further. And because they split further, you see that actually 6a was actually the product of all 4 of them. So now you can see that this times this is ij I bar j bar. So ij I bar j bar. And this times this is also I bar j bar. So these two product is equal to these two products. So the unique factorization really occurs at the level of ideals. If you go back to integers and work with ideals, you will recover your original unique factorization statement. So we are not saying anything new for integers, but for these kind of sets, this is a new kind of statement because it's saying that we still have unique factorization, but if you work at the level of ideals. And in fact, one can show that these are irreducible among all ideals. All right, so last, sorry, I'm stretching it a bit, but this is where really the points come into play, is that a very similar thing holds for x adjoint square root of x cubed minus x. So one can again simply explain in terms of ideals, but in this case it has a geometric meaning, and I will now explain that. Very last step, sorry about that. So to do that, one has to look at the following analogy. Take a look at, the analogy is the following. First, let's go back to the case of all polynomials over the real line. Then we saw that, in fact, actually, what we saw was that there are a lot of irreducible elements here, and there were some quadratic, but a lot of linear irreducible elements, and these are the linear irreducible elements. And in fact, the linear irreducible elements are in 1-1 correspondence with points in A, because what is the correspondence? Given the linear element, you look at its zero. Look at the zero locus of the zero of that, the root of that. But in fact, you can also say this in terms of ideals, because given an element A, if you look at all the functions, all the polynomials which vanish at A, that gives you not only x minus A, but it also gives you all multiples of x minus A. Every multiple of x minus A vanishes here. So the ideal generated by x minus A has the property that it consists of all functions which vanish at A. Keeping this analogy in mind, I want to first argue that this collection of functions is nothing but polynomial functions on the curve y square is equal to x cubed minus x. And I have drawn the curve here for you. Y square is equal to x cubed minus x roughly looks like this. On this curve, call this as y. So this is y here. Then on this curve, y square is x cubed minus x, clearly. So therefore, you can see that if you look at all possible polynomial expressions in this, that is, if you look at all polynomial, that's exactly the set of all polynomial functions on this curve. Polynomial functions on this curve means look at a polynomial in x and y and restrict it to this curve here. So one can easily argue that that is nothing but this collection here. So this collection is a set of all polynomial functions on this. And if you give me a point here, a comma b, what are all polynomial functions which vanish there? What you can easily show is that that will contain x minus a, because clearly x minus a vanishes. It will also contain y minus b. And in fact, it will also contain all the linear combinations, and these are the only ones. So these are all the polynomials here which vanish at the point a comma b. So sorry, that's the last part. And once you appreciate this, then you can see what is happening. You can figure out what is happening. Basically, you can say that the ideal generated by, so therefore, first thing is that the set of all functions which vanish at the point a comma b is giving me this ideal which is not generated by one element, because it's hard to expect one function to determine a point here. I mean, one function whose zero will determine a point here. You need at least two functions to get a point here in most of the places. So for most of the points on the curve, you need at least two functions to determine the point of the curve. Whereas on the line, just one equation is enough. Whereas here it's very unlikely. Most of the time you need at least two equations to determine a point. And the simplest two equations I can think of are x minus a and y minus b. X minus a equal to 0 and y minus b equal to 0. If I put both these equal to 0, that will determine the point here. So this kind of gives an explanation for this other factorization. Where did it go? We had here y times y, same thing. Y times y is equal to x times x plus 1 into x minus 1. What you can show is that the ideal generated by y is a product of three irreducible ideals like this: x comma y times a, x plus 1 comma y times a, and x minus 1 comma y times a. And this has a geometric content to it, namely y equal to 0 is the x-axis, and it's cutting it in three places. And so the coordinates of the 3 points are Oh, this picture is wrong here. Sorry. Something went wrong. Yeah, actually, this y-axis should have been here. So it's 0, 0. So sorry, I'll have to draw the y-axis here. This is the y-axis. Never mind. And so it is 0, 0, 1, 0, and minus 1, 0. These are 3 points, and corresponding to that, I have xy, x plus 1y, and x minus 1y. And the product of these 3 ideals will turn out to be y, all multiples of y in this ring. And that the geometric content is that the y equal to 0, the x-axis, intersects the curve in these 3 points. Similarly, the x equal to 0, that line cuts this curve in this origin, but it's tangential. So it is I1 squared, and this is I2 squared, and this is I3 squared. And now you can see that y times y is x into x minus 1 into x plus 1. The ideal generated by y times y is the same as ideal generated by x into x plus 1 into x minus 1. And you can see that now the unique factorization holds, and it just turns out to be I1 squared, I2 squared, I3 squared, and I1 squared, I2 squared, I3 squared on both sides. So sorry, the last part was a bit too abstract and fast, but I'll stop here. Thank you.
Thank you very much. This was absolutely a wonderful lecture. I think the chat was very engaged today, right from start to the finish. There were so many questions being asked and answered in the chat.
I hope that does not reflect on the fact that I didn't explain some things properly.
Oh, no.
Never mind. And I was just joking. Okay.
They were carrying along from what you said, and it was amazing chat to read. And so if you have any more questions, now maybe the time to ask. And so maybe I'll just get started. So maybe type your questions in the chat or unmute and raise hand. So the one question that I got, are there structures for which the unique factorization does not hold, even when we consider the ideal view? If so, is there a fix to it?
Yeah, so as you move ahead, basically the unique factorization gets replaced by a similar looking statement. It's called primary decomposition, and that holds for, so for example, look at things like polynomial in 2 variables. So let's bring 2 variables with no relations between the variables, so absolutely independent variables. Then if you work with ideals, you can't expect unique factorization here, but you do have what is called as primary decomposition. So that's a similar statement, slightly more complicated. So I don't want to write it right now, but you can look it up. So this the analog is what is called as primary decomposition. Basically, once you move into higher dimensions. Also, I should mention that for these situations, even working with ideals will not work. So you have to rectify them by including more integral elements. So that is one thing. Here, you will not have unique factorization of any kind. You have to. You do have. I guess you will still have primary decomposition here. So that's probably a more general statement. So I should just say maybe this is the answer I will give. In general situation, it's primary decomposition of ideals. So it will basically look like something like your ideal I is some. So you would like to say some irreducible ideal to the power something times product. So first thing is the product is too strong and will not hold. And so what you do is you replace it by intersections. And then so you would like a statement like this, but even this where P is your irreducible ideal is, well, okay, this also where irreducible are called prime actually. So even this needs a little bit of modification. So I think best I'll leave it to you to look up what is primary decomposition of ideals in ring theory, and you can get from that the general answer.
And there's one more question that came up just now. So how different is primary decomposition from prime decomposition?
Sorry?
How different is prime decomposition from primary?
Primary decomposition generalizes prime decomposition. I mean, it's so in the situation where we were looking at in all these cases, these are also primary decompositions. So whatever we have done so far, these are all special cases of primary decomposition. So it generalizes the prime factorization for all these unique factorization situations. It also generalizes this kind of factorization that I'm trying to hint at here. So it generalizes these also. So this is a general thing.
Okay, thank you. And I think one final question is one would expect after this lovely exposition. So are there some other places where they can read up a little bit? Maybe some references which you can suggest?
Sorry, are there some places where read up? Huh?
Yes.
Yeah, so I would suggest reading any books in abstract algebra. So I can suggest the authors, but almost any algebra and more, specifically the ring theory part in these textbooks. Or you can also try to look at books on ring theory, but I think the books on abstract, because this is a very elementary part of ring theory, so much of it you can find in just books in abstract algebra itself. And so if the standard texts are by Artin and Dummett and Foote, Hungerford, etc. First time. So all these standard books in abstract algebra will have it first time. To some extent or not. I mean, some of the topics may be missing. So like the last topic, primary decomposition, probably you may not find in all the books. For that, you'll have to look at books specific to ring theory. And but first, as a for the initial part, at least you can look up all these books. They will all have definitely the initial 70% of the lecture they will have.
Thank you. So I think so. If you have any more questions, do feel free to write to us on our email ID, and we can get them answered. And so once again, do join me in thanking Professor Suresh Nayak for this beautiful tour of abstract algebra that he gave us. And I'm sure it has got many of you thinking, specifically say with the sum of two squares problem or the uniqueness of factorization, what irreducible elements are, and all this. So these are definitely surprising the first time we see it, or at least the first time I saw it, I was genuinely stunned. So overall, the talk was, I think, a perfect mix of rigor and intuition and problems to think about for this audience. So thank you very much once again.
Okay, thanks.
Thank you, sir. So we meet again today at 6:30 p.m. for the very last lecture of STEMS 2022 qualifier camp. So at 6:30 p.m., Professor Ramurthy of Queen's University will be giving us a talk titled The Art of Research. So hope to see you all there. Thank you very much. Many thanks coming to you from the chat.
Okay, thanks.
Thank you, sir.